This is lesson 2 from chapter 17, and we'll be talking about equilibrium constants. The idea of an equilibrium constant, the molarity of the products divided by the molarity of the reactants, was introduced in chapter 16. Here, we apply that idea to weak acids and weak bases, and then in chapter 18, we will apply it to weakly soluble salts, called KSBs. Now, you might remember from chapter 3, a long time ago, that the conductivity of a solution depends upon how many charged particles there are in the solution. The more charged particles there are, the easier it is for the solution to conduct an electrical current. We would call whatever substance you put in the water that yielded a lot of charged particles a strong electrolyte. Right there. And of course, if the substance that you put into the water did not yield very many charged particles, in other words, did not break up into cations and anions very much, then you would have, by definition, a substance that you would call a weak electrolyte. Remember, the word electrolyte refers to the substance that you put into the water, not the solution itself after the substance is in there. Now, a strong acid or a strong base is going to completely dissociate in water, 100% dissociation. If you think about the water molecule as being polar, like you should, that can yank on other positive and negative charged particles with a certain amount of strength or oomph, those particles that have a very weak bond or connection between the cation and the anion will easily be yanked apart. And those particles that have a strong bond or attraction between the cation and the anion will not be easily yanked apart. That's the difference between a strong electrolyte or a strong acid or a strong base or a strongly soluble salt. It has a weak attraction between the cation and the anion. A weak acid, a weak base, a weakly soluble salt will be a weak electrolyte because of the fact that it has a strong attraction between the positive and negative particles, the cation and the anion, and as a result, it's difficult for the water molecule to yank them apart. And if you pardon the pun, this is true every day of the week. I left a pause there for a groan. Now, if we move on a little bit, given the fact that strong acids, strong bases, strongly soluble salts will dissociate 100% or close to it, weak acids, weak bases, and weakly soluble salts barely dissociate at all, 1% or less. There aren't a whole lot that are going to be in between those two numbers. Now, a couple of observations. A strong monoprotic acid. Remember the word mono, one, proton or protic, one proton. When you hydrate it, when you take that proton and you combine it with a water molecule, you get your hydronium ion. And if you only get one of those when an acid dissociates, we say that's a monoprotic acid. And if it's a strong monoprotic acid that dissociates completely, the concentration of the original strong acid equals the concentration of the protons, that is to say the hydroniums, which equals the concentration of the anions, the other part of the molecule, which in this case would be spectator ions. So, for example, if I have 100 HCl's, I'm going to get 100 H pluses and 100 Cl minuses in the solution. So if my original concentration, for example, was 0.1 molar hydrochloric acid, that means I have a 0.1 molar concentration of hydrogen ions and a 0.1 molar concentration of chloride ions. And if I wanted to find the pH of this strong acid, the negative log of 0.1, remember 0.1 is 10 to the negative 1, the negative log of 10 to the negative 1 is 1, pH of 1. And since this has one significant digit, incidentally, by the way, that means the correct answer would be 1.0, because only the digits after the decimal point are significant when you do a logarithm. Now, if I have a weak acid, my concentration of hydrogen ions is going to be substantially lower than the original concentration. For example, if I had a 10th molar solution, let's say of acetic acid, C2H3O2, I'm not going to get a 10th molar hydrogen ion concentration and a 10th molar acetate ion concentration, because they won't all split up. The bond between the hydrogen and the acetate is pretty strong. So maybe 1 in 100 might dissociate. So my concentration of hydrogen ions is going to be substantially less than 0.1. And my pH, therefore, will definitely not be 1. So, to wrap that idea up, how do you know then, without actually doing an experiment or using a pH meter, whether an acid is strong or weak, whether a base is strong or weak? And the answer is there aren't a lot of strong acids and there aren't a lot of strong bases. Memorize the strong acids. So the strong acids are these three right here. These are hydrophilic and, hydrohalic. Halic comes from the word halogen, because these are all in column 7, the halogen family. Then you've got nitric, you've got sulfuric, and you've got perchloric. Those are the 6 you got to know. As far as your strong bases, the strong bases are pretty much the hydroxides of your alkali metals. Group 1A are the alkali metals, especially sodium and potassium being the most common. Maybe coming in 3 would be lithium, and after that, rubidium and cesium. And you have a couple of alkali earth metals, group 2, particularly strontium and barium. So those are the ones that you ought to know. Now, when we write our equilibrium constant, since my equilibrium constant is the result of an ionic compound like a weak acid or a weak base or a weakly soluble salt, since my equilibrium constant is the result of an ionic compound, that equilibrium constant is more specifically called an ionization constant. But it is determined exactly the same way as chapter 16. You put the products in the numerator and make sure you multiply them. Don't add them. I see that on occasion. And you put your reactant in the denominator. But you don't use liquid water, because the idea of the molarity of water dissolved in water is nonsensical. So that would be my equilibrium constant expression for a weak acid. simply called the Ka. And the Kb is done the same way. You put your compound that has gained a proton in the numerator, and the hydroxide that's left when water donates a proton, also in the numerator. The original compound goes in the denominator, and again, you don't use water. That's the Kb. A couple of observations. We'll see a whole table of these acids and their conjugate bases coming up. Point number 2, right here. A large value of K indicates that ionization products are strongly favored. Obviously, then, a weak value of K means the reaction doesn't go to the right very far. And you're talking about a weak acid. Also notice that the weaker the acid, the stronger its conjugate base. The stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid. The weaker the base, the stronger its conjugate acid, as you go from left to right in an acid-base reaction. Please keep in mind that the acid and base, when they're there, are always on the left side of the arrow, the equilibrium sign, and the conjugates are always on the right side. Another helpful point. You will always have reactions that will go from strong to weak. And the things that are strong will always be on the same side of the equilibrium sign, and the things that are weak will always be on the same side of the equilibrium sign. You will never be in a situation where you have something that is strong becoming something that's weak, and something that is weak becoming something strong, which means you don't know which way the reaction will go. It'll always go from strong to weak. Or it'll go that way, depending upon which side is stronger. When the acid and base are the stronger, you get this. If the conjugates are stronger, you get this. So here's that chart I mentioned earlier. The first thing you should notice is that the strongest acids are in the upper left. And so those strongest acids are going to have their weakest conjugate bases. So right across for them will be our weak conjugate bases. There's my weak conjugate bases. There's my strong acids. This hydronium ion over here would probably also include the hydrobromic and the hydroiodic, the other two strong acids. Coming down to the bottom of the page, here's where you would have your sodium hydroxide and your potassium hydroxide and your lithium hydroxide as your principal strong bases. Those would be the most common. These other strong bases, which are becoming weak acids, if we go that direction, those are pretty exotic, unusual. So again, we can expect reactions to go from strong to weak. If you identify an acid or base on the left side as being stronger than its conjugate on the right, then the reaction will go from left to right. If you identify a conjugate acid or a conjugate base on the right side as being stronger than the acid or base it came from, then the reaction will go from right to left. And it's interesting to note that nature has lots and lots of acids and bases, especially weak acids and weak bases. Strong acids and strong bases very readily dissociate, and as a result, those ions typically are going to find other ions to make salts out of. And you have some very important weak bases in nature as well, particularly ammonia, which is a weak base that you often study in biology. Because ammonia, right here, as well as the ammonium ion, and sometimes nitrates and nitrites, are ways in which nitrogen manages to move around in biological systems and the environments in which those biological systems live. So in the atmosphere, of course, you've got diatomic nitrogen gas. And you might remember that that's a very, very strong triple bond. Very, very difficult to break that bond, since it makes up about 79% of Earth's atmosphere. It creates an extremely stable atmosphere, enabling us to have plenty of much more reactive oxygen gas, which we obviously need in order to breathe. This is exquisitely well designed, our atmosphere. And of course, you expect nothing less from the Creator. The problem, though, comes in when how do you get nitrogen into plants and animals? Because proteins are made out of amino acids, and nucleic acids like DNA and RNA also have nitrogen in them. And so you've got to get nitrogen from this form to this form. And that's one of the things that you learn about in biology, is how the nitrogen gets incorporated, first of all, into the soil in nitrogen compounds. And oftentimes there are bacteria that play a role in that. And then once you get these ions like here, they can be absorbed into plants. And then, of course, animals can eat the plants. And then other animals can eat the animals. And as a result, then we get these nitrogen compounds into plants and animals where they can be turned into the necessary proteins and nucleic acids necessary for life. But then, of course, during metabolism, you produce nitrogenous wastes, and now you've got to get rid of that nitrogen. Ammonia takes an awful lot of water to get rid of. And as a result, you only see that system of getting rid of ammonia straight in fish, because the fish are in lots and lots of water, at least if they want to survive. Whereas animals can get rid of their nitrogen in nitrogen compounds like urea or uric acid, which concentrate that and you don't need as much water. Also, if you look down here, if I knock off this hydrogen and replace it with a methyl, or knock off that hydrogen and replace it with a phenyl, I am creating other kinds of molecules that have a similar structure to ammonia and are also organic bases. Now, what about polyprotic acids, which we talk about a lot more than polyprotic bases? Polyprotic acids have multiple protons that they can donate. If we look at phosphoric acid, you've got 3 protons that you can donate. You can donate the first proton here, leaving behind 2. And that happens pretty readily, 10 to the minus third. So 10 to the minus third, if we round 7.5 up to 10, 10 times 10 to the minus third equals approximately 10 to the minus second, which means about 1 in 100. 1 in 100 of H3PO4 molecules will dissociate like this. Now, once you create this, and we bring it down here, you can donate the next proton. And this isn't going to happen much at all. It's important to notice that when you go from minus 3 to minus 8, that means that losing the second proton is 10,000 times less likely to happen. So you don't even have to worry about it. The only time that you're going to start to lose the second proton to the water molecule, the only time you're going to do that is if you're adding a base. In other words, if you're titrating, which we get to in chapter 18. Because every time you add a base with its hydroxides, you create water. And when you create water, it drives the reaction to the right, so you can lose the second proton. And if you did not follow that logic, I encourage you to back up the screencast a little bit and go through it again. What about the next one? So we have one proton left right there. And so if we come down to the next page, I have one proton left. We can donate that proton right here. There's the third proton that picked up a water molecule along the way. And now I have no more protons left. And now here's another 10 to the fifth times less likely to happen than losing the second proton, which was 10 to the fifth times less likely to happen than losing the first proton. So the only way you can keep driving this reaction to the right is by adding a base. And we get to that when we do titration. Now, a device that chemists often use when they talk about acids and bases and their relative strengths is to take the negative log, not of the hydronium hydroxide, which you learned about earlier in the chapter, but to take the negative log of the Ka. Because the Ka or the Kb almost always are very, very small numbers, 10 to the minus 3, 4, 5, 10, 15, 20, and so forth. And so sometimes it's easier to talk about the negative log of them, and you're going to get numbers like this, which is a lot easier when it comes to talking about their relative strengths. And we'll be doing a lab on finding the pKa of an acid, hopefully, within the next month. By the way, just like multiplying Ka times Kb equals Kw, and remember that Kw equals 10 to the minus 14th at 25 degrees. That's a nice little thing to keep in mind. We can also talk about the pKa and the pKb as adding up to 14, just like the pH and the pOH add up to 14. All right, let's take a look at this chart right here. Which of the following is the strongest acid? Now here's the trick, because this is on the test. We might ask ourselves this quick question: where did hydrofluoric acid come from? Well, it could have been something that was mined, or it could have been something that was produced in the lab. You know that a acid plus a base can equal a salt or produce a salt. Well, that will come in handy a little bit later when we try to find out the pH of salts. But in this review section, it's quite easy, and that is all we have to do is recognize that every one of these is an acid because they have a proton that can be donated. In your organic compounds, that proton, by the way, is the hydrogen that's connected to an oxygen, not the hydrogens connected to the carbon. And so if we wanted to find out which of these is the strongest acid, now that we know that they're all acids, all we have to do is to go up to the chart, and I won't go back a few pages, but the ones that are highest in the upper left of the chart are your strongest acids, and then you identify the others from the chart as you go down the chart, and they get weaker and weaker and then you can rank these. You can also go to the right side of the chart and look at the conjugate bases. So I'm going to stop this screencast right here, and we will pick up with section 17.5 later.